Assignment 2.2, Libby Ferguson. My instruction. Steady state exercise is a balance between the energy required by the working muscles and the rate of oxygen circulating the body to get to the muscles. On graphs, you'll be able to identify steady state, as the results will plateau as the muscles' demands have been met. Heart rate. I predict that the heart rate will increase quickly at the beginning of exercise. However, it will then plateau. Heart rate. There will be an increase due to the anticipatory rise. The emotional stimuli will detect that the body is about to exercise. The stimuli will then stimulate the release of adrenaline, which will increase the heart rate. At the start of exercise, it also increases. This is because the receptors, your chemoreceptors, proprioceptors and baroreceptors, will detect an increase in chemicals, movement and blood pressure. The receptors will send an impulse to the sympathetic nervous system, which stimulates the SA node, causing an increase in heart rate. However, it will plateau after a while due to the working muscles' demand for oxygen being met with a sufficient amount of oxygen as the athletes performing steady state exercise. This means the chemoreceptors will no longer be detecting a demand for oxygen, so it won't send an impulse to the cardiac control centre.
Stroke volume. It's the amount of blood pumped out of the heart in one beat. There will be an increase due to the increased amount of venous return. This is because the working muscles' demand for oxygen has increased due to the increase in intensity of exercise, so more blood will be returning back to the heart. The heart fills with more blood, so that more is able to circulate around the body. However, stroke volume will plateau as the intensity of exercise remains constant as it reaches steady state. The muscles will be supplied with sufficient oxygen, so the heart no longer needs to keep increasing the amount of blood that gets pumped out. The average stroke volume for an adult at rest is 70 millilitres, whereas an elite athlete such as Mo Farah's is 110 at rest. Cardiac output. The amount of blood pumped out of the heart in a minute. This will increase as there will be an anticipatory rise pre-exercise, which will increase both stroke volume and heart rate. This will increase the cardiac output as the muscles will begin to demand more oxygen as the intensity of exercise increases. Once the intensity of the exercise plateaus and has reached steady state, the muscles' demand for oxygen will no longer increase. Therefore, no more blood needs to be pumped out per beat. The average cardiac output for a person at rest is 4.9 litres per minute, whereas an elite athlete such as Mo Farah's is 3.63 litres per minute. Blood flow. Once exercise starts, the receptors will detect changes in the body. The chemoreceptors will be detecting an increase in oxygen as the working muscles begin to need more oxygen. The proprioceptors will detect an increase in movement, and the baroreceptors will detect the increase of blood pressure. These increases will cause an increase in the heart rate as the muscles need more oxygen. This means they take priority, so the blood vessels vasodilate and vasoconstrict, so that more blood flows to the muscles, so respiration can take place quicker. The vascular shunt is the distribution of blood around the body, and during exercise it redistributes the blood to the areas that require the highest level of oxygen. For example, during exercise, this is the working muscles. Blood pressure. The force and rate of the heartbeat and the diameter and elasticity of the arterial walls. At the start of exercise, the blood pressure will increase. There is a greater increase in systolic blood pressure than diastolic blood pressure. To help reduce blood pressure, blood vessels will vasodilate. However, at the start of exercise, there is an increase in cardiac output, which will increase the blood pressure. The blood pressure will plateau once steady state is reached, as the cardiac output will plateau, as the demand for oxygen from the working muscles has been met. Thermoregulation. At the beginning of exercise, your body will begin to heat up due to the muscles contracting. There will be an increase in thermoregulation due to the body beginning to sweat as it tries to cool the body down. There will be an increase in the plasma volume in the blood, which will help to support the sweat glands when the body heats up, which will help to control thermal regulation. Venous return. There will be an increase as more blood has to flow back to the heart once exercise has started, to then be distributed back out to the body, to the working muscles. However, when the athlete reaches steady state, there will be a constant supply of blood flow back to the heart. The heart rate will plateau, so there won't be an increase of blood circulating around the body, so venous return will plateau. Starling's law. This implies that stroke volume will increase in response to the heart filling with blood. So therefore, Starling's law is dependent on venous return. This means that at the start of exercise, the increase in venous return will also increase the stroke volume. When steady state is reached and venous return plateaus due to cardiac output, so will stroke volume. Tidal volume is the amount of air breathed in and out in a single breath. At the start of exercise, it will increase due to an increase in the demand of oxygen from the muscles. It will then start to plateau due to the muscles being supplied with the sufficient amount of oxygen, so therefore tidal volume no longer needs to increase, as it will stay at a constant level. Breathing rate. Breathing rate will increase at the beginning of exercise due to an emotional and volitional stimulus. An impulse will then be sent to the DRG and then down the intercostal nerve, which will cause the external intercostal muscles and diaphragm to contract, which will increase the breathing rate. The peripheral feedback also helps to control the breathing. For example, the chemoreceptors will detect changes of chemicals in the blood, such as an increase in oxygen, as the muscles will begin to demand more. Once the athlete reaches steady state, breathing rate will plateau because the muscles' demand for oxygen will no longer increase as the intensity of exercise is staying constant. The chemoreceptors will then be detecting the same level of oxygen in the blood, and the proprioceptors will be detecting the same amount of movement as the intensity isn't getting harder. Therefore, they won't send impulses to the DRG to increase the contractions of the respiratory muscles. The normal breathing rate for an adult at rest is 12 to 20 breaths per minute, whereas an elite athlete would be lower, as their intercostal muscles and other respiratory muscles, such as the diaphragm, would be stronger, so they don't need to breathe as much. Oxygen dissociation curve. The blue line on the graph shows what happens to oxyhemoglobin saturation during exercise, whereas the red line is at rest. During exercise, the graph shifts to the right as there is an increase in the temperature and an increase in acidity in the blood. The increase in temperature is caused by the muscle contractions, which produce kinetic energy, which also creates heat energy. There is an increase in acid during aerobic exercise, as the waste products of respiration, so carbon dioxide and hydrogen, cause a reaction in the bloodstream, causing the pH in the blood to decrease, making it more acidic. This shift to the right causes more oxygen to be released from the hemoglobin, as the oxygen in the oxyhemoglobin is replaced by hydrogen, and this oxygen gets released into the working muscles so that they can respire, producing energy for the muscles to keep contracting, allowing the athlete to carry on exercising. Muscle spindles. Muscle spindles are found in your skeletal muscles and are a type of proprioceptor. They detect when the muscle stretches and help to resist the stretch. When they detect this stretch, they will send information to the spinal cord. There are secondary sensors which will detect how big the stretch was. These will then send information to the central nervous system, informing them of how big the stretch was. The central nervous system will then send this information to the motor neuron, telling the muscle to contract, as this will reduce the stretch. Golgi tendons. These are receptors that are activated by the muscle stretching. They receive information from the tendons about tension and stop overextension. Aerobic energy system. The aerobic energy system produces ATP, and it uses 3 reactions to do so. The first is aerobic glycolysis. As oxygen is present, the pyruvic acid bonds with the coenzyme A to form acetyl-CoA. The second reaction is the Krebs cycle, which uses the acetyl-CoA from aerobic glycolysis, which then combines with oxalic acid, forming citric acid. This citric acid is then oxidized as oxygen is present. This oxidization reaction forms 4 compounds: carbon dioxide, which gets breathed out of the body, hydrogen, 2 ATP molecules, and oxalic acid. It is known as the Krebs cycle because the reaction produces oxalic acid, which means it can continue to combine with the acetyl-CoA, which was produced during aerobic glycolysis, to produce citric acid, which then forms the Krebs cycle again. The third reaction is the electron transport chain, which uses the hydrogen that was produced in the Krebs cycle. This hydrogen then binds on to NAD and FAD, which are transport enzymes. This then produces NADH and FADH. The hydrogen molecule is split into ions and electrons. The hydrogen ions are oxidized and form water, which gets removed as you breathe out. The hydrogen electrons produce 34 ATP molecules. In total, the aerobic energy system produces 38 ATP molecules, and it lasts for 3+ minutes.